But the exam, which is 1 week from today, is on chapters 8, 9, 10, and 11. It's not the stuff that we're doing today.
Facebook. Yeah, I was gonna try to get a study group going for Monday or Tuesday.
Okay.
Yeah. Tuesday. That's good. Yeah, if you're at MGC, you can consider doing group study or something.
So we're talking about solutions, calculations involving solutions in this chapter. And used throughout, what you guys should have seen in your previous chemistry, and which you have seen in lab, I know, is molarity, the unit of concentration. Definition of molarity, the symbol for that is capital M. It's equal to moles of the solute over the liters of the solution, where the solvent is the substance that's present in greatest quantities. In aqueous solution, that's solutions like you guys deal with, that'll be water. The solute is everything else. And the solution means the solute or solutes plus the solvent. So this is moles of the thing that's dissolved divided by the per liter of everything in the solution. Another unit of concentration, you'll see, is mass percent. Which is that. Mass of the solute divided by the mass of the solution times 100. And molality. So molality, you may or may not have seen already. The symbol for that is a lowercase m as opposed to the capital M for molarity. And it starts out the same way. Just like molarity, it's moles of solute at the top. But the denominator is different. In molarity, it's liters Here it's kilograms, there it's solution, here it's solvent. So the solvent by itself. Okay. So with these definitions, we can start looking at a few examples. All right, so here, for example, I tell you the mass percent of hydrochloric acid in a solution, that's obvious, and I give you the density. And we want to calculate two things. You guys know what the brackets mean? Concentration and molarity, right? Right. This is just the way of saying what's the molarity of the hydrochloric acid. And then the molality also. So, what do you think? How are you going to approach this? Kilograms. But do we know how many grams?
Do you assume 100 grams of solution and then
There we
find
do
the
that, absolutely,
moles?
yes. And then do what?
Find the moles of hydrochloric acid.
Okay. So then we'll know, okay, what Josh is saying is, what I think, sounds like it, just concentrating on this first, right? Let's look at the definition, right? Remember moles of solute over liters of solution. In this case, the solute would be hydrochloric acid. So we need two numbers. We need the moles of hydrochloric acid and the liters of solution. If I don't tell you how much it is, right? But if we assume, how much did you want to assume?
100 grams.
100 grams of solution, then we know how many grams of hydrochloric acid, 38 grams, right? And if we know grams, well, then we can get moles, right? And because we're assuming, we can make it exactly 100 grams, so we don't have to worry about our sig figs here. This is because it's 38% hydrogen chloride, hydrochloric acid, and if we assume 100 grams, it's just that's the grams of hydrogen chloric acid. And then Josh wanted to convert to moles using the molar mass this way. Where this is the molar mass of hydrochloric acid, 35.45 for chlorine plus 1.01 for hydrogen. 2 places passing this one. And that gives us this, right? So now we know that. What about the liters of solution?
Use the density.
Use density, right? We know that the solution is 1.1886 grams per cubic centimeter, which is the same as a milliliter, right? And we assumed 100 grams, so we can just use the density to find the volume. And so we got so we just took the mass of the solution divided by the density. That gave us the volume in cubic centimeters, and there's 1,000 cubic centimeters in a liter, so we get this many liters. The reason I converted it to liters is because that's what the definition says. So we see that the concentration of hydrochloric acid in that solution is 12.39 mole. You guys all right with that?
Yeah.
And then second part, part B, asks for the molality. And the definition of molality is moles of solute per kilogram of solvent. We already know the moles of the solute. We figured that out already, so let's just carry that over. What we're going to do here is, because the solvent's water, we can assume at least to 3 significant figures that the density is 1 gram per milliliter. See what was the volume. It's 12.39 mole HCl. That should be stuff you guys have seen before, right? Just refresh your memories. This also is nothing really new, but it's an example of the type of problem you should be expecting. This next one right here.
Is it just coincidence that the molality and the molarity are the concentration?
Not quite coincidence, but it doesn't always turn out that way. Okay, so this one, it's not as complicated as it might look, but you have to kind of follow the chlorine through the whole process. So you start out with 150 milliliters of a 10% by mass sodium chloride solution, which means we can figure out how much sodium chloride is in there and how much chlorine is in there, right? How much of the chloride ion. We give you the density and the mass. And then we do some things to it. We perform some chemical reactions. We acidify it. Then we treat it with excess manganese 4 oxide. And when we do that, it ends up that all the chlorine ion, is released as chlorine gas. So we took this much sodium chloride with this much chlorine, treated it, turned all of this chlorine into chlorine gas. Now we trap that chlorine gas. And then we put in excess hydrogen gas. We react the chlorine with the hydrogen and make hydrogen chloride gas. All of the chlorine reacts. The key to this is to follow the chlorine. In every step, all of the chlorine, wherever it is, its reactant is going to the next step. Then we take that hydrogen chloride gas and we dissolve all of it in enough water so that we have 250.0 milliliters of a solution with hydrochloric acid. And what we want to do is find out what the concentration of hydrochloric acid is in that solution. So it kind of looks like this. So it really doesn't matter, but what happens is, so our goal is to calculate the concentration of hydrochloric acid over here, and the definition of molarity is moles of solute, which is hydrochloric acid, per liters of solution. You know how many liters of solution you have. It's 250 mils or 0.2500 liters, right? So all you have to figure out is how many moles of hydrochloric acid made it over here. Okay? Now, because there's 1 mole of hydrochloric acid for every 1 mole of chlorine, because of the formula, if we know how many moles of chlorine made it over here, we know how many moles of hydrochloric acid there are, and we can do the calculation. So all we have to do is follow the chlorine from here all the way over here. Well, we don't have to worry about these intermediate steps because in every single step, all of the chlorine react. Chlorine always goes to the next step. So if we know how much chlorine we have here, that's how much chlorine we have here. You guys see that? So all we have to do is figure out how many moles of chlorine we have over here. There's enough information there to do it. That gives us moles of chlorine, which is the same as moles of hydrochloric acid. Just divide by 0.2500 and we're done. So it looks complicated, but it's not really. Because there's 1 mole of chlorine for every 1 mole of sodium chloride. If we know how many moles of sodium chloride we have here, we know how many moles of chlorine, which means we know how many moles of hydrochloric acid we have at the end, right? So now you guys tell me, how are we going to find out how many moles of sodium chloride we have here?
10 grams.
10 grams?
When you just
Well, there's 10 grams
by mass
per
and then
100 grams of solution, right?
then divide that by, we just divide that by 22.98 to get the moles.
So, let's see. So if we have, here, this is a little bit different than that previous problem because now we have a specific amount of solution, right? So we're going to use the density here to figure out how many grams of solution we have first. Once we know how many grams of solution we actually have, then we use the 10% to get the grams of sodium chloride. And then that's sodium chloride, right? So it's not going to be 22.99, but it's going to be sodium chloride, which is 22.99 plus 35.45 here. So So when we multiply the density times the volume, that gives us the mass of the solution, grams. It's 10% sodium chloride by mass. Times 10 over 100. guys understand what we did so far? Brandon?
How do we know the masses whole solution?
We took I gave you the volume of it, and I also gave you the density. So density times volume is the mass.
I mean the second part, under the NaCl, is that just the 58?
The molar, this is the molar mass of sodium chloride, this number right here?
Yeah.
So
No,
This one?
Yeah, that right there.
This right? Oh, it's 10% by mass, which means there's 10 grams of sodium chloride per 100 grams of solution.
Okay.
That's what the percent by mass means. Yeah, this is from the definition. Anything else? So now we know how many moles of sodium chloride we have. Because there's 1 mole of chlorine per 1 mole of sodium chloride, we know how many moles of chlorine we have. Because there's 1 mole of hydrochloric acid for every 1 mole of chlorine, we know how many moles of hydrochloric acid we have. And I'll actually do all these conversions even though the numbers won't change, so you see the units. That means we know the top part, and the bottom part I gave you, 250 mils. You guys see how that works? It's similar to that problem that we worked out on Monday, where we followed the nitrogen from the fruit set into the metatoluidine. Remember that one? Pretty much the same idea. We don't need the details of the intermediate reactions as long as we can follow one element from beginning to end. Next week in lab, yeah.
If, let's say, instead of it was just 1 to 1,
Right.
if it was like 1 to 2, would you multiply it by 2?
Yeah, see,
Or
yeah,
divide it
good.
by 2?
That's why I wanted to show these, because, so you get them in your notes.
Mhm.
Because let's say it was, I don't know, like calcium chloride, so hydrochloric acid, CaCl2. Then it would be 1 mole of calcium chloride per 2 moles of chlorine. So in that case, you divide by 2. As long as you have that stoichiometry from the formula, you can do it. Any other questions? Next week in lab, you guys are doing experiment 14, which is, by the way, not the title that it says in the syllabus. In the syllabus, it says something like quantitative solutions or something, but it's the spectroscopy of the cobalt-2 ion. It's experiment 14, so if you just find experiment 14 in your lab manual, that's the right one. But when you do that lab, when you set up the calculations for that lab, there are several dilutions that you're going to be doing. And so you'll be using the dilution equation, which you should have seen already, but so the dilution equation is M1V1 equals M2V2. All this is saying is that, okay, so first of all, it only applies to situations where the only process that's happening is the amount of solvent is changing. The only thing that can change is the amount of solvent. You can be either adding more solvent, that's dilution, or you can be taking solvent away, concentrating it. It still works. So what this is saying is the molarity of the first solution times its volume in liters. Okay, molarity is moles per liter, right? If you take the moles per liter times the liters, that's just saying that the moles that you have initially is equal to M2V2, the molarity of the second solution times its volume in liters. Moles per liter times liters. All this is saying is that the moles of the solute stays the same because you're not changing it. You're adding solvent, or you're taking solvent out, but the solute stays the same. Does that make sense? In this example, start out by making the solution an aqueous solution of potassium phosphate by dissolving 124.3 grams of solid potassium phosphate in enough water, dissolving it, bring it up to a total volume of 1 liter of solution. Then, what we do is we evaporate 125.0 milliliters of water from the solution. And what we want to find out is, after we've done that evaporation, what the concentration of potassium phosphate is, what the concentration of the potassium ion is, and what the total concentration of ions in that solution is. What do you think we should be doing?
And moles of potassium phosphate.
Sure, because we're going to find the initial concentration, right? One of the things that's going on is the amount of solvent's changing, right? I'm taking 125 milliliters of the water out by evaporating it, which means at one point we're going to use the dilution equation.
It's all good.
So we're finding moles of potassium phosphate by taking the mass divided by the molar mass, then dividing that by the volume of solution, which is just 1 liter. That part okay with you guys? Then what we do is we evaporate 125 mils of the water. So here's where the M1V1, M2V2 equals M2V2 comes in. This is going to be our M1. What we want to find, okay, the concentration of potassium phosphate after we do the evaporation is M2. We rearrange that equation. Okay? So we know what M1 is. What's V1? Yeah, it's 1 liter, right? Because we initially had a liter. What's V2?
125 liters.
How much?
Probably 125 liters. 875.
Yeah, it's 875 mils. It's right. It's 1 liter minus that, right? So it's 0.8750. You know what M1 is? Make sense so far? Good. So now we know the answer to the first question. What's the concentration of potassium phosphate in the more concentrated solution? And it should make sense. If we're evaporating solvent, then the concentration should be greater, right? And 0.669 is greater than 0.5856. Now, how about the concentration of potassium ion? What do you know about potassium phosphate? Soluble or insoluble? Soluble, right? Yes. Yes. It's soluble because potassium, if potassium, sodium, lithium, potassium, or ammonium is the cation, it doesn't matter what the anion is, it's soluble. There's a rule about phosphate, but it's trumped by the rule for potassium. So we know that this is soluble. We also know this. If we had 1 mole of potassium phosphate dissolved in solution, how many moles of potassium ion would we have?
3.
3, right? Because there's 3 moles of potassium and 1 mole of potassium phosphate. So what that means is the concentration of potassium ion, let me see if I can make this short. The concentration of potassium ion will be 3 times the concentration of potassium phosphate. You guys buy that? So in terms of making the units work out, this is how you write it. But you guys agree that it's just 3 times that, right? That's 2.01 molar. So it's 0.669 molar in potassium phosphate, 2.01 molar in potassium ion. What about the total, the last one here? The total concentration of ions in that solution. What do you think?
Would ions be
It's all the ions, so that means cations and anions, right? So we've already, go ahead.
that'd be positive potassium ions plus the phosphate.
Yeah, right, plus the phosphate anion, right? Yeah, you're right. Okay. Does that make sense to you guys? Total concentration of ions is going to be all the potassium ions plus all the phosphate ions. So if we had 1 mole of potassium phosphate, how many moles of ions would we have? 4. So all we have to do is take the concentration of potassium phosphate and multiply it by 4. That make sense? No?
Yeah.
Yes. In terms of the units, it looks like this.
It's 4 ions because there's 3 plus potassium ions and there's 1 negative phosphate.
Yeah. So 2.68 molar in ions. So that's kind of the units of concentration and how you can be expected to see, be expected to work out problems with those. Now, let's talk about when we dissolve, what happens when we dissolve something in solution in water. We take an ionic compound that's soluble, like sodium nitrate, sodium chloride. Chapter 15 will talk a little bit more about what the crystalline structure of sodium chloride actually looks like, but for now, it's sufficient to think about it as alternating sodium ions and chloride ions in the 3 dimensions. Or it's also coming out of the board towards you and going back into the board. The idea being that like charges want to be as far from each other as they can, so all the cations want to be as far away as they can from each other, and the anions also, the chloride ions. Yet at the same time, they want to be as close to oppositely charged ions as they can. So the sodium ions and the chloride ions are trying to be as close to each other as they can. So it ends up with a structure of something like this. We take a crystal of sodium chloride, drop it into water. You guys know that water is polar. Dipole moment with a negative charge up here by the oxygen, positive charge somewhere down there. So what happens is there's this attraction between the negative end of the water molecule and the sodium ion. That attraction is weaker than the attraction that the chloride ions next to the sodium ion, there's one out here and one in the back of the tube, have. So that's not strong enough to start doing anything. But the thing is, water is the solvent. That means there's a lot more water than there is sodium ion right there, right? Sodium chloride. So there's a bunch of them. They start ganging up on that sodium ion. And pretty soon, the sum of their attractive interactions is enough to start pulling that sodium ion away from the chloride ions in the crystal. Something like this. And when this sodium ion starts getting pulled away from the crystal, there's room for more water molecules to start surrounding it and start pulling on it. And they can actually start working their way in here, between the sodium ion and the rest of the crystal. And pretty soon, that sodium ion is completely surrounded by water molecules. and they're coming out here and back to the board. Matter of fact, okay, for the sodium ions, the oxygens will be pointed in towards the sodium ion, and it forms more or less a sphere around that ion. It's called a sphere of solvation, sphere of nitration. Chloride ions, same thing happens, only the water's flipped around, right? The positive end of the water molecule is going to be pointed towards the chloride ions. You get something like this. So, and once that happens, then we have the ions surrounded by water molecules, which means that they're free to move through the solution. They're going to drag a cluster of water molecules with them, but they can move. We call a solution like this an electrolytic solution. And that term comes from electrolytes, or term electrolytes come from this experiment right here. Any of you guys seen this one before? Okay. This is just a regular incandescent light bulb right here. And the way an incandescent light bulb works is that when you plug this into a socket, electrical current runs through one of the prongs, up through one of these wires, through this filament, right? Usually it's a tungsten filament here. And then, as long as there's a complete connection, it runs up the other side, down the other wire, and down and back into the wall, to the ground. And as this current is being pushed through the tungsten wire, the filament here, there's a lot of resistance. And so when you try to force electrical current through a wire like that with the resistance, it heats up. And when it heats up, it gives off black body radiation, which is light. It gives off light. So it glows, right? In order for this to work, okay, there has to be a complete circuit. If you break the filament, then you don't see any light because there's not a complete circuit. The current's not going all the way through. It's not heating up. The way this apparatus is set up is that the current has to run through either side. It doesn't have to be both. Either side or the other, right? There's two wires, right? These two wires have to somehow conduct a current. We have a current, electrical current. A flow of charge has to get from one to the other. And then there's a complete circuit, and the filament here will glow. So what I have here is I have some solutions. I have sodium chloride. Regular sodium chloride, solid. And what I'm going to do is I'm going to plug this in. Well, it's close to you guys. Oh,
There's one right here on the ground.
yeah, well, I don't think it'll reach though. And then if I put it down there, you can't see it. It's all right. I'll do it over here. Make sense of it over there? Just went over and did it. Okay. Yeah, this will work. Which is more boring, watch me untangle a cord or listen to chemistry? It's a close call. And so it's not glowing now, right? Plug it in, it's still not glowing. And so this is sodium chloride. Will glow if I use this? Is there any way I could make it glow with that?
Watch your fingers.
My fingers, yeah. Other than water. It's except for this is connected. Melt it. Who said melt it? Yeah, exactly. If I were to melt this, I'd have you can do it. Melt molten sodium chloride. It'll conduct a current. For sure. But let's just take some water. This is deionized water I got from Brian's lab. I'll just put deionized water in there. And I don't see anything, right? Right? So it's gone, right? Which means that there's a complete circuit. So somehow current is getting from one of these wires to the other. That's the only way that light bulb is going to glow. And it glowed pretty brightly. It ends up that, well, first of all, knowing how the light bulb works, it makes sense, I think, that the more current that you're trying to force through that wire, the brighter it's going to glow. Right? And so the more current this solution can carry, can allow to travel between the wires, the brighter that light's going to flow. Sodium chloride dissolves pretty well. We learned in the solubility rules that it's soluble. Okay? We'll keep it at that. Let's try acetic acid. This is acetic acid. It's 0.1 molar acetic acid. Doesn't seem to be glowing. Well, yeah, it is a little bit. Can you guys see it up front here?
Not really.
Not really? Okay, I need to turn out the lights. Lights. No, I'd probably touch the wires. Yeah. Can anybody get like a back door or something? Or there you go. Thanks. Hi, phone.
Oh, there you go.
Right? Okay. So now you believe me? It's glowing? Not nearly as brightly as the sodium chloride solution was.
What's this one?
That was acetic acid. Acetic acid, yeah.
0.1 molar acetic acid, right? So this is what we call a weak electrolyte. I'll talk about that in a second. Just to make sure that we're comparing apples to apples. And this is a saturated solution of sodium chloride. This is really a lot of sodium chloride. I'm going to take a 0.1 molar solution of sodium chloride and compare it to the 0.1 molar solution of acetic acid. Okay, same concentration, right? One barely glows. We had to turn out all the lights to see it. This one glowed pretty brightly. So that means that one of those, the sodium chloride solution, has to be allowing more current to flow, carrying more current than the other. And the only way that can be is if there are more ions in the solution. What's carrying the current, the charge, from one of those wires to the other are the ions, right? The more ions you have, the more charge can flow from one wire to the other. The more charge that can flow, the brighter the light bulb. Make sense? So what that means is, because these two solutions are the same concentration, there's 0.1 moles of acetic acid per liter of solution, there's 0.1 moles of sodium chloride per liter of solution. There aren't as many ions in the 0.1 molar solution of acetic acid as there is in the 0.1 molar solution of sodium chloride. The only way that can be is if the acetic acid molecules aren't, all of them aren't dissociating. Matter of fact, it ends up that, in particular for acetic acid, only 1 out of every 10,000 or so molecules actually dissociate. Show it like this.
Does that mean you have a stronger bond?
Compared to the interactions of the water with the ions, comparing that to the strength of the bond between the hydrogen ion and the acid ion, yeah. So, acetic acid looks like this. It's an organic acid, it's carboxylic acid. So when you put acetic acid in water, it dissociates into the acetate ion and hydrogen ion. But up to now, I've always used just one arrow pointing that way. Now I'm using 2 arrows. What the 2 arrows show you is that you can think about this as going both ways. A molecule of acetic acid dissociates, but then the hydrogen ion and the acetate ion can also recombine to reform the acetic acid molecule. And this is going on constantly in that solution, but it's at equilibrium. It means that, if you were to follow a single molecule of acetic acid, only 1 out of 10,000 in this compound is going to be dissociated. 9,999 or so are going to still be the acetic acid molecule. But if you follow that molecule long enough, you'll probably be able to see it break apart into acetate and hydrogen ion. And if you kept following the acetate ion, eventually you'd see it recombine with the hydrogen ion and reform acetic acid. Okay, that kind of makes sense? See, another one. Now let's try this sodium acetate. Sodium acetate. So this is the sodium ion, cation, and the acetate anion. What that means is that must dissolve to a greater extent than the acetic acid, right? Because it glows brighter. There's more current. That means there's more ions. This is also 0.1 molar, by the way. Ammonium hydroxide, 0.1 molar. You can See it? Do I need to turn off the lights again?
No, I see it.
Yeah, you don't.
No, I did.
Were you traumatized last time? But it is glowing. You guys believe me?
Yes.
But not much, right? It's pretty much like the acetic acid was. So this is the acetic acid, 0.1 molar. This is ammonium hydroxide, 0.1 molar. Again, you know, we had to turn off the lights to see it,
I
right?
can see that.
Now I'm going to mix them together. Chemical reaction occurs. Okay. Why do you think that happened? It's what?
Which two compounds were it?
Double replacement.
Double replacement. And what happens when that double replacement occurs? I mean, you're right, it's a double replacement reaction, right? But why would that make more current flow when each of those was a weak electrolyte, right?
Because of
The molecules were able to displace farther apart.
Yeah, pretty much, right? But specifically, what's that?
Isn't it making it look like it's an acid base, so water is penetrated, so you've got what we were talking about before with the electrolytes?
Yes. Yeah, well, yes. It's an acid-base reaction, and that's what makes a salt plus water, right? And so, let's look at this. So it's acetic acid. Plus ammonium hydroxide. Makes a salt plus water. What's the salt?